Lesson 3, Situational Problems. Our goal is to analyze and interpret situations represented by relations and functions. When dealing with a situational problem, you must decide if there are any restrictions on the domain or the range. This means, are there any elements or numbers that would not be allowed or not apply to the situation? For example, if we were talking about a situation that involved time, we would say that the domain is restricted to positive numbers because negative time does not make sense. This graph shows the number of fishing boats, N, anchored in an inlet in the Queen Charlotte Islands as a function of time. Part A, are there any restrictions on the domain or the range? So first of all, let's look at the domain. Our domain deals with time. As soon as we see time, we know that there is a restriction because we can't have a negative time, so it must be positive. For the range, restrictions on the number of boats. Again, negative number of boats doesn't make sense, so they must be positive. But we further have a restriction on the range because we also can't have fractions of boats, so they must be whole numbers. Why are the points on the graph not connected? So the reason that these points cannot be connected is because of that idea that we have to have a whole number of boats. If we connected the boats, it means that we could go out and count half of a boat at a given time. Part C, determine the domain and range of the graph. So let's look at our domain. Because it is a set of points, our domain should be listed out. So what are all of the different times that we have? Well, our first time on our graph is 9 o'clock. So I didn't need this comma to start with. 9 o'clock is our first one. We have data points at 10, 11, 12, 13, 1400 hours, 15, and 16. And that's our last data point. So instead of writing out, I've just wrote out the first numbers, right, instead of writing out the zeros at the end. Our range is the number of boats. So if we start at the bottom of our graph, the fewest number of boats that are in that inlet at any time are 6. We don't have any data points that represent 7, but we do at 8, at 10, 11, at 15, and at 25. The Great Wheel is being built in Beijing in the People's Republic of China. When finished, it will be the largest Ferris wheel in the world. The wheel will have a diameter of 193 meters and will reach a maximum height of 208 meters. The graph shows a rider's height relative to the ground for a 20-minute ride through one rotation. What are the values of points A, B, C, and D, and what do they represent? So let's look at each of these. Point A is up here. So point A would represent the maximum height. We need to be able to know what that maximum height would be. Well, that maximum height tells us in our word problem that they'll reach a maximum height of 208 meters. And I could write it on my graph over here. Part B, or point B, is down here. Point B would be the initial height on the ride. And how high is that initial height? in our question, it tells us that that wheel has a diameter of 193. So if we look at this picture, that means from here to here is 193, but we know that this maximum height is 208. So if we do 208 subtract 193, we end up with an initial height then of 15 meters. Part C, or point C, is down here. Point C is our initial time, and the initial time would be 0. And lastly, point D represents a time, and it represents the end of the ride. And in our question, it tells us that the ride is 20 minutes long. Part B, what are the domain and range of the graph? So our domain is the x values, which in this case isn't really x, but it's time. It's our horizontal values. So our domain goes from 0 to 20 minutes and includes every number in between, so we can use square brackets. The range would be our height. The lowest height on this graph would be 15 meters, and we go all the way up to a maximum of 208 meters. Again, those 2 points are included, so square brackets. Our next example. When police officers investigate a car crash, they estimate the speed of the car was traveling by measuring the skid distance. Part A. Why are the points on this graph connected? So first of all, let's look at speed. Our speed can include all numbers in between. We don't just magically change from 40 kilometers to an hour to instantly traveling 60 or instantly traveling 80. Looking at the skid distance, again, if we have a skid mark, it can be every number in our graph as long as they're positive values. So the increase in speed and time are continuous. Part B, estimate the domain and range of the graph, and are there any restrictions on the domain and range? So let's first of all look at the domain. Writing our domain in set notation, all of our points are in between 40 and 120. There's dots on those two, so they are included, so square brackets. Are there any restrictions on the speed? Speed has to be positive values. Doesn't make sense to have a negative speed. There would also be a maximum speed that the car could travel. And there would be a minimum speed that would produce a skid mark. And if you're traveling very slowly and you slam on the brakes, you still won't make a skid mark. Let's look at the range. Our range on our graph, our lowest point is down here, with the highest one being up here. So our lowest point in the range would be just below 20, so perhaps about 18. The highest point is just above 140, so I estimated it at 142. Are there any restrictions on the skid distance? Skids could not be negative, so the skid numbers must be positive. Can you think of any others? In math, a graph provides much information. This graph shows the depth of a scuba diver as a function of time. And here's a series of questions. So the first one says, how many minutes did the dive last? Well, from start to finish, the dive took 30 minutes. At what times did the diver stop her descent? Well, she wasn't getting any deeper in two different sections of our graph, those two. So she didn't get any deeper between 4 and 8 minutes. And again, from 10 to 14 minutes. What was the greatest depth the diver reached? So the maximum depth would be 20 minutes. And part B of that question says for how many, not 20 minutes, but 20 meters. And part B says how many minutes was she at that depth. And so we can look on our graph and see that she was at that depth between 10 and 14 minutes. So she was there for 4 minutes. The last question is, are there any restrictions on the domain or range? Both the domain and range, so the time and depth, would have to be positive numbers. There would be a maximum depth that she can safely scuba dive. There would also be a maximum amount of time before she ran out of air. Let's make some connections looking at a couple of other examples. So the properties of a graph can provide information about a given situation. So we've already talked about kind of just reading values, but how steep lines are indicate how fast something happens. So this is a distance time graph. If we are starting here and we compare this section of graph compared to this section of graph, the blue section is a steeper increase than the green section. So that means that this object would be traveling faster in the blue section than it was in the green section. And so we can talk about steep increases, areas of no change, moderate increases, or slow decreases. Each point on this graph represents a bag of popcorn. Explain the answer to each question below. So let's see what data we can find. It says, which bag is the most expensive? So cost is on our vertical axis. Point C is the highest one, so that would be the most expensive. And what does it cost? Well, reading across on our graph, we can see that it would be $7. In part B, which bag has the least mass? Mass is along the bottom of our graph, and the smallest number that corresponds to a point would hit our graph about here. So it would be bag B. And how much is that mass? Well, it's between 400 and 600, so probably about 500 grams. Part C, which bags have the same mass? So we're looking for 2 points that line up and would have the same mass, so D and E, and that mass would be about 1,800 grams. Part D, which bags cost the same? So we want to read the other way on our graph this time, and if we look at A and E, would cost the same, and their cost would be $4. Part E, which bags, C or D, have the better value? So let's look at what's happening. Part C, costs us $7, but we get 1,600 grams, whereas part D only costs us about $5.50, and we get more. We get 1,800 grams. So bag D would be the best buy because we get more grams for less money. This graph shows the volume of water in a watering can can change over time. First question, what is the starting volume? So the starting volume is at time 0, it would be 1.0 liters. Which point is this? Point A. Describe segment AB and what that means. So segment AB is this part of our graph. It's an increase, and we're just going to call it a moderate increase. What this means is that more water is being added. So somebody's filling up the watering can. Describe segment BC. So the next section is between here and here. So there's no increase. And this means that the volume of water stays the same. Describe segment CD. So CD is this part of our graph. And this is a steeper decrease than AB. And that decrease in water means that the water is being dumped out or being emptied. What does point D represent? So point D is down here at the bottom of the graph, and point D would represent the time to empty the can. Which is at or after 90 seconds. One final example for today. Josephine leaves her home and walks to the store. After buying a drink, she slowly jogs to her friend's house. Josephine visits with her friend for a while and then runs directly home. Using the distances shown, draw a distance time graph that shows Josephine's distance from her house and explain each section of our graph. All right, so we're just doing a sketch, so it doesn't have to be super accurate. We're going to do distance along the vertical axis and time along the horizontal. So this is the distance from home. When we're drawing a graph, it is important to label what our graph is talking about, as well as both axes. So point A, or the starting point on our graph, would be when Josephine decides that she's leaving home. She walks 1 kilometer to the store. Now when she walks to the store, and so we want that to be kind of a moderate to low increase. So point B would be when she reaches the store. So let's keep track of these as we go. Section AB is when she walks to the store. Once she gets to that store, our question tells us that she buys a drink. So her distance isn't going to change while she's in there buying a drink. So it's going to stay flat as time continues. So from BC, she's buying a drink. After she buys her drink, she slowly jogs to her friend's house. So if she's jogging, it means that the line should be steeper than when she walked to the store. The friend's house is another 3 kilometers, so that means that she's going to travel a total of 4 kilometers from home. So we need her to end up here, and it needs to be a little bit steeper than her walk. So here's point D. So between C and D, she jogged to her friend's house. When she gets to her friend's house, she visits for a while, so her distance is not going to change. She probably visits longer than what she took to buy the drink, so that section of our graph should be slightly longer. So DE is when she visits her friend. And then after her visit, she runs home. So again, because she's running, it should be a steeper line than her jog. So we want, and it's going to come all the way home, so it needs to come all the way back down to the bottom, and that would be at point F. So section EF is when she runs home. Okay, there's some practice for you now.